Hello everyone. In the previous lecture of nuclear reactions, we discussed the energetics of nuclear reactions. We discussed the Q value, the threshold for a nuclear reaction, whether it is for a charged particle induced reaction or neutron induced reaction. So all the energetics, the feasibility of the reaction was studied in that part. In this lecture, I'll be talking about the cross-section for the nuclear reaction, how to determine the probability of a nuclear reaction and what are the different types of reactions that take place when you use neutron and charged particle as projectiles. So let us talk about the cross-section. The cross-section, which we denote as sigma, is a measure of the probability of occurrence of a nuclear reaction. So that is the point to note, that what is the probability of occurrence of a nuclear reaction, which we represent by sigma. Or to talk in very simple terms, it is the cross-sectional area that the target nucleus will offer to the projectile. It is a very simplistic way of telling the cross-section. In fact, from that only the cross-section derives its units of barn, where one barn is 10 power minus 24 centimeters square. So the nuclear dimensions are of the order of Fermi's 10 power minus 13 centimeter. And so in fact the R0, the radius constant, is 1.4 10 power minus 13 centimeter. And the radii of nuclei will be R0 a raised to 1/3. So that will be about 10 to the minus 12 or so on. So accordingly, the nuclear area, the cross section of a nucleus, if you just cut a cross section, the circle pi r square will be of the order of 10 to the minus 24 centimeters square. And the unit of cross section, that's why it's called as a barn, when barn is 10 power minus 24 centimeters. So it's a very simple way of telling the cross section. There are many more things which will come in actually defining the cross section of a nuclear reaction as we go along. So how do we use the nuclear reaction, cross section in the nuclear reactions when we want to write the rate of a reaction? So depending upon whether we are doing neutron induced reaction or charged particle induced reactions, the terms that come into the formulation of nuclear reaction rate will be slightly different, which I try to highlight here. So the rate of a reaction for neutron induced reaction is called n sigma phi, where n is the number of target atoms per centimeter cube. In fact, actually it is not that way. It's total number of target atoms. N is the total number of target atoms. Because in case of reactor neutron, suppose you have a reactor neutron, entire target is exposed. So all the atoms in the target are exposed to neutrons. And so n sigma phi, n is the number of target atoms, sigma is the cross section. So unit is sigma square, centimeter square, and phi is the flux. So how many neutrons are going through a unit area per second? That will define the phi. So n into sigma into phi, flux is the rate of a reaction, that is the rate at which, so if you see here, the units will match atoms into centimeter square into neutrons per centimeter square per second. So it will be centimeter square, it will be atoms per second. So this many atoms are formed per second. That is the rate at which the reaction takes place. In the case of charged particle induced reaction, the charged particle induced reaction will be having sort of a, if you have a target, you don't have a sea of charged particle, but you will have a beam which will bombard the target. So in the target, only a small area is exposed to the beam. And therefore, the number of target atoms is not defined total number of atoms, but it is the target atoms per centimeter square. The unit area, how many atoms are present in the target. Sigma is the cross section, and now beam, the target, that whatever is falling on the beam and the target is now not per centimeter square per second, but it's the number of particles falling on the target per second. So there is a slight change in the units of flux or the particle intensity. In the case of neutrons, it was flux, neutrons per centimeter square per second. In the case of charged particles, it's the particles per second. So both the units, both the reaction rates ultimately will come out to be atoms per second. You can see here n sigma I will be number of atoms per centimeter square into centimeter square into particles per second. It will be again atoms per second. In both the cases, whatever way the units of target atoms and the flux or the intensity, we always end up with the n sigma phi or n sigma I as rate of the reaction. Now, as I mentioned, that the cross-sectional area offered by the nucleus, target nucleus of the projectile is a very simplistic way of defining the cross-section. Essentially, if you see when the projectile hits the target, depending upon the distance from the center of the target nucleus, there will be different, the different angular momenta are involved. So, in actually, when you define the nuclear reactions, we have particles carrying certain amount of angular momentum. And that angular momentum will be defined in terms of the r into p, where r is the distance, radial distance from the target center. Let us say this is the target center and this is the projectile going. So this is like the r. So b is nothing but r sine theta. So v is called the impact parameter and p is the momentum of the particle. So r cross p is the angular momentum. R into linear momentum is called the angular momentum, and angular momentum is a quantity in nuclear reactions which dictates the different types of mechanisms of the nuclear reaction. So p, the distance, the vertical distance from the target center to the wave at which the projectile is coming, will call as the impact parameter, and this impact parameter essentially is the r into sine theta. So this is like if it is here, then this is the r and this is theta. So this is the r sine theta is the impact, the vertical distance from target center to the distance of the projectile from the center. Now the linear momentum can be written in terms of the de Broglie wavelength h cross by lambda cross, where lambda cross is the reduced wavelength of the projectile, and the angular momentum can be written LH cross. So essentially, angular momentum in terms of linear momentum can be now written as LH cross equal to BH cross by lambda cross, and so the impact parameter B equal to L into lambda cross. So this impact parameter B essentially is a classical quantity at what distance from the target center the projectile will hit the target center, where it will hit the target, that will be the impact parameter. And L is how much is the angular momentum the projectile will bring in the units of lambda cross. So essentially, classically you can see the B can take any value, and so the angular momentum can take a continuous values. But then that the angular momentum is quantized in quantum systems, and so quantum mechanically certain values of B will correspond to one value of L. So L can vary from 0, 1, 2 and so on, H cross. So you try to have a correlation between the continuously varying impact parameter and the discrete values of L, which I have tried to explain using this. So this is, suppose this is the target nucleus here, cross section of the target, and if that projectile hits at the center within this radius, that is the radius of 1 lambda cross, that we will call L value equal to 0. So we call it a S wave particle. If it is within the next one L lambda cross, L equal to 1, L equal to 2, L equal to 3 and so on. So depending upon at what distance the projectile is hitting the target nucleus from the center, we can bring in different amount of angular momentum. And the one which is at the maximum of the target radius will be the Lmax. So let us now try to calculate the cross section for a particular L value. So it is like the annular area of this annulus. So from L equal to 0 to L equal to 1, we'll say L equal to. So 1 lambda, 0 lambda to 1 lambda to 2 lambda, that is L equal to 1. So this is what I try to calculate here, the angular momentum dependent cross section sigma L. So for a particular concentric ring, the sigma L will be area of the outer circle upon area of the minus 1 upon area of the inner circle. So pi L plus 1 lambda cross square minus pi L lambda cross, where L lambda is the impact parameter. So you can see here, you can take the pi lambda cross out, and so you are left with L square plus 1 plus 2L, that is L plus 1 square minus L square. So it will be pi lambda cross square 2L. So now you can see the cross section for a particular L wave depends upon L value, pi lambda cross square 2L plus 1. And since these charged particles are now, they can penetrate the Coulombic barrier, so there is a transmission coefficient. Even for the neutron, there is a change in potential, and hence there is a transmission coefficient factor. That is defined in terms of the transmission coefficients. TL is called the transmission coefficients for L, particular L value. So now this is the actual definition of the cross section. Lambda sigma L equal to pi lambda cross square 2L plus 1 TL. So let us now try to see, for the total reaction cross section will be the sum of the angular momentum dependent cross section for all L values up to L max. So L max will be R by lambda cross. So we can sum the, so the reaction cross section sigma R will be pi lambda cross square sum over all the 2L plus 1 values. 2L plus 1 is for one L value, so sum over sigma of 2L plus 1. Let us forget about the TL value for the moment, and so we can write it as summation over 2L and summation over n 0 to L max will be L max plus 1. So when you say 0 to L max, so when we sum 1 that many times, will become L max plus 1. When you sum L over this one, you will get 2 into summation of L. So now we can write this as pi lambda cross square. Summation of L will be n plus 1 by 2. So it will be 2 is outside, L max into L max plus 1 by 2 plus L max plus 1. And so now you can see L max is square plus 2L max plus 1. This whole thing will be L max square plus 2L max plus 1, that is L max plus 1 whole thing square. And the L max you can write as R by lambda cross, because L max equal to R upon lambda cross. So it will become R pi lambda cross square L by lambda cross plus 1. And so you can see here that it will become R by R plus lambda cross upon lambda cross. Lambda cross will cancel with this one. You will have pi R plus lambda cross square. So sigma R essentially is pi R plus lambda cross square by summing over the sigma L values from 0 to L max. Now let us discuss these cross sections for neutrons and charged particles separately, because the cross section varies in a different fashion for neutral particles like neutrons and the charged particles. So just now we saw sigma was nothing but pi R plus lambda cross square. So for the case of neutrons, sigma n can be actually written as pi R plus lambda cross square, R plus lambda cross square. So here the rate of the reaction then will be in terms of n sigma phi, where n is the number of target atoms for neutrons, and phi is the flux in terms of neutrons per centimeter square. Now let us go a little bit deep into how the neutrons are captured by the nucleus. See, for a neutron-induced reaction, which are always exoergic. Exoergic means whenever a neutron is captured by a nucleus, energy is released equivalent to the binding energy of neutron in that nucleus. So neutron plus target nucleus has higher mass compared to the neutron, the compound nucleus that will be formed. So suppose you write this in the energy terms. So this is the mass of the neutron plus target, and this is the mass of the nucleus that is formed. For example, if you say neutron plus 59 cobalt, then this is 60 cobalt in its ground state. So when the neutron is captured by cobalt 60, this much energy is the binding energy that is released, and so this cobalt 60 will be excited with this much energy of the order of 7 to 8 MeV, and this excited nucleus then can emit by gamma ray, or it can have other channels also. So neutron-induced reactions, particularly the neutron capture reactions, when a neutron is captured by a nucleus, they are always exergic, and the energy released is equivalent to the binding energy of neutron in that nucleus. The cross-section for such reactions, neutron-induced reactions, you can see here, sigma n is decreasing with the increasing energy of neutron. In fact, it is called the 1 by v, where v is the velocity of neutron. So neutron-induced reaction cross-sections, the low energy neutrons are having highest cross-section. I'll be explaining this very soon. And at certain intermediate energy, there are resonances. These resonances correspond to the nucleus populated in certain discrete energy states. So this is like a resonance. When the neutron energy is such that the compound nucleus populates in certain energy level, then you will get a jump in the cross-section. When it is somewhere here where there is no level, cross-section will not be that much high. Okay, so now why this cross-section is falling with the increasing energy of neutron. At low energy, the neutron wavelength of the neutron is lambda cross is much larger than the nuclear radius. You know that neutrons are used for neutron diffraction studies, where the neutron diffraction means the crystal's dimensions of the order of angstroms. So a low energy neutron, thermal neutron, will have the wavelength of the order of dimensions of the atoms. So this is much larger than nuclear dimensions, and therefore you will find that as the energy of the neutron is increasing, wavelength is decreasing, and so the cross-section is also decreasing, to put it in a very simple way. So for low energy neutrons, in fact, now you can see here, this is the target nucleus, then L equal to 0, because first wavelength itself is more than the dimension of the nucleus, and so you will have mostly 0 S wave neutrons. So cross-section can be written as pi lambda cross square T0, L equal to 0. And as the energy of neutron increases, lambda cross, the reduced wavelength decreases, therefore the cross-section is decreasing the energy of neutron. So what are the different types of reactions that can occur with the neutrons? Most important reaction that takes place is called the neutron capture, or it is called the radiative capture. Radiative capture means when the neutron is captured by a nucleus, the nucleus that is formed, compound nucleus, will emit gamma rays. So that is the radiation, gamma radiation. And so neutron capture followed by emission of gamma ray is called radiative capture. And this kind of reactions are most common with thermal neutrons. And as you will always see that when you add a neutron to a stable nucleus, we are increasing the neutron to proton ratio, and therefore most of the products of N-gamma reactions are beta minus active, because we are producing a neutron rich isotope. For example, 197 gold N-gamma, 198 gold, and this 198 gold will be beta minus active to decay to 198 mercury. So with the heavier nuclei like cobalt, gold, uranium, tin, lead, the N-gamma is the most used common reaction. But when it comes to low Z target nuclei, sulfur, silicon, magnesium, then you will find the reactions where charged particles are emitted, NP reaction, neutron capture followed by proton emission, neutron capture followed by alpha emission. So this kind of reactions are possible with the low Z target nuclei, because the Coulomb barrier for emission of protons and alpha are not very high. Whereas for heavy nuclei, the Coulomb barrier for emission of alpha and protons are quite high, and so such heavy nuclei do not undergo N-gamma type of reaction, but the light nuclei can undergo N-gamma type, this N-alpha and NP type of reactions. When you go to still heavier elements like actinides, then the thermal neutrons can induce even fission, because the fission barriers are low for actinides, and so upon capture of a neutron like 235 uranium, even thermal neutrons can induce fission in the heavy nuclei. Now, when you see, depending upon the energy, the types of reactions that take place with neutrons, neutrons are classified into Thermal neutrons having energy less than 0.5 electron volt. Epithermal neutrons, epithermal means the a region where it is slightly higher than thermal and there are resonances in the cross sections as a function of energy of neutron, 0.5 electron volt to about a keV of energy, and then more than 1 keV are called fast neutrons. So you can see here that the thermal neutrons are most reactive, and this classification actually has come from cadmium. Cadmium is absorbing all the thermal neutrons. So if you wrap a sample with cadmium foil, all thermal neutrons are captured and then the sample will not see the thermal neutron. So from that this classification has come that if it is less than 0.5 eV, then energy that is called as the thermal neutron. So we classify it into three zones: low energy zone where it is 1 by V law, the resonance region, and the fast neutron energy region. Just to explain why cross-section for the neutron reaction follows 1 by V, if you recall, we said 1 by V law and then the resonances. So we try to explain using the transmission of neutron through the potential well. The cross-section for the neutron, total cross-section is pi r plus lambda cross square, and for low energy neutrons we said that lambda cross is much larger than the radius of the nucleus. So you can actually set up an equation for transmission of the neutron. Neutron is like a wave and going to hit the nuclear potential of the nucleus. So at initially you have a plane wave e raised to I kx, and once it is captured, the energy of neutron is much higher. So inside the nucleus is called e raised to I capital Kx. So there is a wave number of the neutron is changing from small k to capital K as it is transmitted through the potential well, and the transmission coefficient is written as transmitted flux upon the incident flux. So general scattering theory of neutron actually can be used to find out the transmission coefficient, and this transmission coefficient can be, in fact, if you solve the scattering equation for the S wave neutrons, because for low energy neutrons the angular momentum is 0, it can be written as 4 small k capital K upon small k plus capital K square. And since capital K is much larger than small k, so inside the nucleus neutron energies are almost 20-30 MeV, and outside it will be thermal neutron. So you can neglect the small k inside the nucleus. So this small k can be neglected with respect to capital K, and so it becomes sigma n pi lambda cross square. 1 k will cancel, so small k upon capital K, and this small k is nothing but related to velocity. So k is actually proportional to velocity, and lambda cross square proportional to 1 by v square. Lambda cross is h cross by mu v, and so it becomes net result is 1 by v. That explains the sigma neutron varying as 1 by v at low energy neutrons from the transmission coefficient. Then for the resonance region, Breed and Wigner gave a formula for resonances for n gamma reaction, which is in terms of pi lambda cross square. The spin of the compound nucleus, the neutron is half spin 2n plus 2s, 2 into neutron spin plus 1, and the spin of the target nucleus 2ia plus 1. The width for the neutron decay to gamma decay plus upon resonance energy epsilon 0 minus epsilon minus epsilon 0. These are the energies, and the gamma by 2. Gamma is nothing but gamma n plus gamma. So these are the gamma. Actually, they are the, if you see the nucleus, the certain levels have their widths. That levels are called gamma. For neutron decay and gamma, for gamma decay, there are the widths of the levels. So the resonance formula essentially is quite accurately predicts the cross sections for the resonances for neutron induced reactions. So we'll not go into details, but I thought it is good to tell you that the resonances also can be explained by Breed-Wigner formula, and the 1 by v also can be explained by the transmission coefficient formula. Now let us come to the charged particle induced reaction. The scenario is different in the case of charged particles because there is a Coulomb barrier, and so you try to consider a charged particle coming to a target nucleus. So there will be a different types of potentials playing into play. One is the nuclear potential, which is attractive at short distances, and there is a Coulombic potential which is repulsive all around. So when the projectile is coming close to the target nucleus, it will experience the Coulombic repulsion of the target nucleus, which starts becoming positive at a longer distance, and as it is coming closer, it will experience the attractive potential to nucleus potential. So the sum total of the repulsive and the attractive potential will be this dashed line, and this shows a barrier which is called as the fusion barrier. So for the light charged particle like proton and alpha, mostly we can say that Coulomb barrier. This can be called as a Coulomb barrier, but when you take heavy ions into picture, then the nuclear potential becomes significant, and so we call it fusion barrier. So right now we will use this as a Coulomb barrier. So this is the barrier the projectile has to cross. So now you see from infinity, the charged particle is coming, and as it is coming down, its momentum. So this is the center of mass energy. Momentum is decreasing, and at contact, the momentum may become zero. So this is what I try to show here. At distance of closest approach, the momentum is root 2 mu ECM minus BC. Normally, at infinity, it is 2 mu ECM, but when it is coming close to the target nucleus, the Coulombic barrier will start getting felt, and so it becomes 2 mu ECM minus BC. You can take the 2 mu ECM square root the half outside, so you are left with 1 minus BC upon ECM to the power half. So this is the momentum at infinity, and this is the momentum at contact. The angular momentum at infinity and at contact has to be conserved, and you take the help of this formalism to calculate L max at contact, R into mu, 2 mu ECM, 1 minus BC upon ECM. So this is R into P, R cross P is the angular momentum. So I have replaced this momentum, the linear momentum at contact, with L max equal to R into that momentum. And so sigma becomes pi lambda per square L max plus 1 square. And since for charged particles, you will find L max will be quite high. So you can say pi lambda per square L max square, 1 can be neglected with respect to L max. So now pi lambda cross square sigma R equal to L max can be written as R by lambda cross or R P by H cross. This P is nothing but the momentum at infinity, momentum at contact. So momentum at infinity into the 1 minus BC upon ECM, and this is nothing but the 1 by lambda cross square, momentum at infinity. So this will cancel with this. So you are left with pi R square 1 minus BC upon ECM. So the cross section for charged particle induced reaction, you can see here with ECM, as the energy of the projectile is increasing, it will go up. So this is the VC. Below VC, the cross section is 0. Above VC, the cross section will increase with increasing energy of the central mass. So this is what is the cross section for charged particle induced reactions are increasing beyond VC. Cross section for neutron induced reaction decrease at 1 by V, then have some resonances. So the charged particle induced reactions typically, when the projectile is coming, it can bombard the target or a compound nucleus. And let us try to see what is the excess energy of the compound nucleus. So we calculate the Q value, mass of alpha, mass of niobium 93, mass of this niobium 97. This will be plus 2.437 MeV. And you can calculate the Coulomb barrier by 1.4382, Z1, Z2, 1 R0, A raised to 1/3, A1 1/3 plus A2 1/3. You can substitute to get 14.05 MeV. So let us try to calculate what is the minimum energy of the alpha that will be inducing the reaction, or the threshold for the Coulomb barrier. So this is the energy available in the center of mass. It will be into mass ratio 97 upon 93, compound nucleus upon target. So alpha particle should have 14.65 MeV energy to induce this reaction. This is the threshold for Coulombic barrier. Let us take a case of 30 MeV alpha particle, which is higher than the Coulomb barrier. So in such a case, excess energy of the compound nucleus will be ECM plus Q. ECM plus 30 MeV alpha, ECM into 93 by 97 plus Q value will be 31.2 MeV. excitation energy. So the compound nucleus 927 technetium will be formed with an excitation energy of 30 MeV, and then this excited compound nucleus can emit neutrons, protons, gamma rays, depending upon the emission barriers and the angular momentum states available. So charge particle induced reactions, a hot excited compound nucleus can emit then gamma ray, neutron, proton. There is a competition between emission of different types of particles. So now you can have proton induced reactions like oxygen 18, PN, fluorine 18, cadmium 111, PN, indium 111. So these are the reactions used to produce useful isotopes like fluorine 18 for positron emitter, indium 111 in nuclear medicine, zinc 68, P2N, P3N, P3N, P5. These are all some of the useful isotopes, how they are produced. Proton is bombarded with target, and that compound nucleus is emitting neutrons. Deuteron-induced reactions, you can have DP, D alpha, DN, and alpha-induced reactions, you can have alpha 2N, alpha 3N, and alpha 4N types of reactions. So these are the kinds of reactions that can happen with the charged particles. The charged particle is forming a compound nucleus, and the compound nucleus can emit neutrons, protons, alpha, depending upon the excitation energy and the available emission barriers for different particles. So I'll stop here and then discuss in the next lecture how to determine the cross sections experiment. Thank you.